So the more hospitals you have to close to.
Remember we did some like
This is like the entire class. You're the key the class will have our own. I didn't reach out to you.
Okay, I think it's time to get started. Good afternoon, everyone, once again. Welcome to Bootcamp. So this is the first bootcamp for the course Introduction to Deep Learning. That's 11-485, 685, and 785. So if you're not enrolled in that course, you're probably in the wrong room. So boot camps are a way to get started with your homeworks. So all of you, I hope, already are aware of this, that homework 1 is out. All the 4 parts, like part 1, part 2, autograd, and the bonus. And so boot camps, we hold boot camps at the start of every homework to help you get started with those homework parts. And from there on, we have hackathons where we usually recommend that you guys get together as groups and study groups and collaborate so that you can pick up on those homework parts much more quickly. So it is the recommendation from all the TAs, from the faculty as well. Try and attend all the boot camps. Try and be here for all hackathons. It's going to be much more enjoyable when you work together and collaborate closely. So today's bootcamp, we'll get started with homework 1. I am joined by my fellow TAs here, Iman, Ramrik, Alex, Kushali, and Leo. Hey guys. So we'll go over how you can get started with homework 1, part 1, followed by part 2, and we'll take questions at the end of the discussion. So today's idea would be, like we discussed how you can get started with building your own neural network in yesterday's recitation. I hope all of you have gone through the recording once, and that will be of immense help in your homework 1, part 2. So with that, I'll hand it over to Iman to go over homework 1, part 1.
Okay, just with like the show of hands, who has actually like gotten time to go over the homework, at least like the write-up so far for homework 1, part 1? Okay, so in general, like we will first go over collaboration policy. You would be assigned to like your study groups. And in your study groups, you're allowed to like help your friends debug code. You're allowed to look at your friend's code. You're allowed to copy math equations from any other source that are not in the code format. You're allowed to look at, but the main problem is you're not allowed to be typing code while you're looking at your friend's code, because it defies the whole purpose of you typing code by yourself. You're not allowed to import pre-built or pre-trained models. And when you guys submit the code, we'll be passing it through the integrity MOS checker. And if we find similarity, you guys will be called out. So make sure anything that you submit is actually your own work. So directions, you're required to do this homework in Python version 3. And in the homework, when you download, you'll have requirements.txt. You're meant to like use that and download all the dependencies in the libraries. We recommend that you look at all the problems before you try to solve the first one, just to get a better idea or gist of like what problem sets are coming and how you're going to manage your time accordingly. And if you complete this assignment before September 6th, it's for like early birds, you will receive like 5 extra bonus points. Yep.
I mean, if you're working in groups and obviously you're discussing ideas together, so the code will be similar. I mean, if you're allowed to look at our.
Yeah, you're allowed to discuss, but you're not allowed to copy code. Of course, like because a lot of things are intuitive and we do have similar like ways to implement those, but it's pretty obvious when someone has actually like copied from someone. Sorry?
That sounds like really great because we're not.
No, as in like, let's say you're in a classroom, right? You're allowed to discuss, let's say you're stuck in like a certain formula or something. You're allowed to go to your friend and ask them like, how did you figure it out? But you cannot exactly look at their implementation and like actually write it the exact same way. Like you should understand what you're writing. And it's pretty obvious when you look at code and like, it's like someone has copied it. So we encourage collaboration, but it's not like you're gonna copy because you want to make sure that you actually understand and you learn.
I can add something to it. So even if you are implementing the same architecture, for example, in your homework part 2, there are multiple different ways of implementing the same thing. Now, if you somehow implement the exact same way of every possibility, then probably you are. And the way, so usually it works the other way around. If you try to implement any research paper, you end up implementing a different way that you probably can't use the same checkpoint of the research paper. That's one way you can think of. If you're able to use the same person's checkpoint in your core, you're probably way too similar to measure work.
Okay, so briefly over the homework objectives, we're going to be writing like different components that you'll be using to build the simple MLP. And then you will learn how to actually chain these components up together to make your functional MLP. We'll learn how to implement losses to train the network parameters. We'll learn how to backpropagate the derivatives of these losses through the network and to compute loss derivatives with respect to all the network parameters. We'll incorporate these derivatives into the SGD optimizer, and then we'll also look at one common regularization technique called batch normalization. And then if you guys have noticed, there's also homework 1 part 1 bonus. In that you will be also implementing another optimizer called Atom, and you will cover another regularization technique called dropout. So we've provided a checklist for you guys as you finish, like this is how the order we'd encourage you to go over to understand like different components. Once you're done with something, you should like be using this as a way to figure out where you are. So like the main idea of like bunch of part 1s is you will eventually end up building your own MyTorch library. And it is something that you'll notice like for other part 1s, we will keep asking you to copy code from homework 1 part 1 because the end goal is that you build PyTorch, which is like our version of the PyTorch library. And then different things that we'll be covering in the library would be MLPs, convolution, yes?
So it's just about the quiz checkpoint, right?
Okay.
It refers to revisit lecture 8 about batch normalization, for example. But in tandem, there's also a bonus submission deadline of September 6th. But
Yep.
lecture 8 happens after that.
Yeah, so you'll only realize this, it only happens for homework 1, and that's the whole point that it's a bonus. So we do actually want you guys to be a bit more proactive, but like keep in mind it's only for like homework 1 where the lectures are like kind of behind the homeworks. So yeah, we would like, we're like intending that you would probably look at the old lecture 8 and understand, or like look at the write-up, reach out to TAs if you want to submit early. So like the different models you'll be covering are multi-layer perceptron, which would be in homework 1, part 1, convolutional neural networks, RNNs with GRUs, LSTMs, and so on. Okay, so going over briefly when you download the tar file from the Autolab, sometimes the tar file ends up having like a .1 or some weird numbers. Make sure to like rename it back to just like homework 1 part 1 handout.tr, so you'll be able to extract it then. In your directory, you would find you have My Torch folder, you'd have Models folder, and inside My Torch, you'll have NN and optimizers. So over the homework, we do tell you which file you should be editing, so it's gonna be pretty easy to like follow through. And then you have autograder flags and autograder.py, which I'll cover in a bit how you're gonna like test your homework. So in the homework, you will notice that it's pretty common, like in DL, that you use a certain way, like notations. So you can always refer to this cheat sheet we've provided if you have any confusion on what the symbol basically means. So you can go over that. So like the overall big picture is that we'll be building different layers. You'll have input layer, and then we have understanding shapes part, where if you're confused about the different shapes, it gives you an idea of here, like the type of shapes you're expecting. So before I give it over to a different TA, I'll go over briefly. Where's the start code? Okay. So if you want to test out like your, let's say, anything specific, this is how your directory will look like. And inside the autograded flags, you can set the flag. Let's say you're done with, I don't know, identity in the activation functions, and you just want to check for that. You can set them true manually here, and then you can go on the terminal and type Python homework 1 autograder.py1, and it should then only test for that. But if you want to test for all of those, you can set all of them to true. So that's the whole point of having like flags here. And if you guys want help with like setting up like Anaconda and stuff, we're expecting you guys to make like virtual environments. And at the end, in the appendix, you'll find different, so depending on what type of machine you have, if you have Windows, Linux, or Macs, we do give you guys like a brief walkthrough of how you're meant to like create your virtual environments and run your code in that to make sure you guys don't run into any dependency issues. And I'll hand it over to the next TA to cover the next part of the homework.
Hey guys, I'll just walk you through the notebook, the first 2 parts. Okay, so this, we'll start with the linear layer. And I think this homework is basically formula to code. So anywhere you see this blue colored formula, you'll just have to code that part. So walking you through there, this is the linear layer, and this is the basic structure which you'll find in your Python file. And you can check your the shape of your variables through this table, which would be very helpful when you try to solve your formulas. And when you if there is a shape error, you can just see what shape you require. This is the formula that you need to convert. This is the forward function. And so let's go to the code for my torch and then linear layer. And here in the forward function, first you'll have to initialize the W, which is the weight matrix, and the B is the bias. Yeah.
Possible to increase.
Is that good?
The size of it, but that's the
Okay.
Can you switch to light mode?
Sorry?
Switch to light mode from dark mode.
Lights.
Where is it?
just lights.
For the code editor, instead of having a dark mode.
Got them. Got this one?
I've never been on the light mode, so give me a few minutes.
Same for all of us.
Yeah. So first you will be initializing the weight and the bias of your linear layer. And so just to see what the shape would be, you can just refer. This is going to be C out cross C in. And the bias would be just C out cross 1. It's a scalar. Then we'll come to the forward function. To initialize A, you can see what the shape of A is. And using that, it'll be very easy for you to, you know, initialize A and then just put in the formula for Z. Similarly, there's a backward function. We have given you all the formulas. There are little more formulas for backward function, but they are pretty easy to implement. Just use this use this formula.
I had a question regarding the formula.
Yeah.
Should I ask now or later?
What's the question? Yeah.
In the previous step, we were mentioning derivatives. Like just if you scroll down, backward function of the formula. Yeah. So you see dou z by dou a, which is basically change in the output with respect to change in the inputs elements. Yeah. And then in the next formula, it just gets converted to your weights. So why does that happen?
Can you repeat again, please?
So if you're looking at dou L by dou A, the first formula, there's the second part of that formula where there is dou Z by dou A transpose.
Yeah.
The entire formula.
Yeah.
And then if you go to the next equation, the one below, where that is the thing that we will implement, that gets converted to weights.
Okay.
Next page. Yeah,
Oh.
here. Why exactly does that happen? I just wanted to understand how we're converting that equation to this equation.
Okay, so the formula for DLDA is like loss into the weight, and
So that's just, a differentiation of the linear transformation of your weighted input. So if you go to the first one, the first equation, before this. When you're doing a forward pass, that is doing a weighted input of your forward function. That is like weights into your inputs plus the bias. When you're going back, you are computing the gradients with respect to mainly three components, which is your weights, your biases, and the input of your previous layers, or basically the output of your previous layers. And that's what A is here. So if you go to the equation before this, you have del Z by del A, and that is just differentiating your forward equation. If you look at the forward equation, you just simply differentiate that with respect to that variable, and that's how you get that equation. Again, I'm just iterating that some of these things might be a little daunting to understand, but all of these concepts will be covered in very detailed manner in the lectures.
So next we'll be implementing the activation function. And there are mainly four scalar activation and one vector activation, which is scalars are the sigmoid, ReLU, tanh, and GeLU. And the one vector would be the softmax. Basically, you can see like these are the graphs for sigmoid activation function, and there are formulas as well given to you. For some of the activation function, you'll have to check Google. Like I think for tanh, we haven't given you formula. For backward function, you can just Google the formula. And for, I think, GeLU, you'll be using ERF, which is the error function, which is available in the SciPy library. Just import that function and just enter this into the into the code. Here, your activation function, you can find them here. We have given you the basic code, so you can just use this code for all the other activation function and just implement the formulas that are given to you. Yeah. Define the forward function as well. and you'll have to replace the formula for z, formula for z dot a with your formula. And I think, yeah, this is going to be the activation function. After you implement your linear layer and your activation function, which is like the basic building block for building your MLPs, we'll start working on the building your neural network model, and we have I think four models. You can find them on mlp.py. MLP0, which implements, which has 0 hidden layer, MLP1, which has 1 hidden layer, and MLP4, which has 4 hidden layers. So these are the 4 MLPs that you will be implementing, and you get the formula here, and you just have to implement it to your code. If there is any question on these 3 parts, I can answer them. Otherwise, Ramrik, you can. Thank you.
Okay. So you have to implement also the loss functions. We have many loss functions that have been asked for you to implement. The first one is the MSC loss function, right? So this stands for mean squared error, and everything related to the equation has been given. So mean square error. So it's first the square, the error square, and then the mean of that. So everything has been put here step by step. So first you calculate the square error, right? So the square error, you have A, which is the model output, and Y, which is the ground truth. And then you want just to see how far the ground truth is compared to the model output. Then you just do, the model output minus the ground truth value, and then you square it somehow. Then before doing the mean, actually, you need to sum that, right? And you can just use matrix multiplication to do that. Here they have used some vectors, some matrices, sorry, full of 1, right, of different shape, and then using this formula, actually, it can sum everything that was in this SE they got here. And then you come to the mean square error, the loss itself, so divided by, the total of things you have in your matrices at the beginning somehow. And then you have to, that was the forward equation. You have to implement also the backward equation for that. So it's just a differentiation. So if you differentiate actually the mean square error formula, right, you'll be having, this 2 times this out of this. So, this is really straightforward, and you will see it in class, in lecture. After that, you have to implement the cross entropy. So the forward equation is also right there, right? You will use softmax in that forward equation, and then the softmax will be used in this formula, and then you get the cross entropy. And then also differentiating this, actually, you will be having, the equation you need for the backward, and then you have to implement it from scratch also. Then the optimizers, right? The optimizers are those functions which will help you adjust the parameter of your model after calculating the gradient. So after now the loss, you have to implement the stochastic gradient descent, right? Here in this homework, you will be more focusing on mini batch stochastic gradient descent with momentum, right? And what momentum does, it helps you speed actually how fast you converge, right, to a global minima, if we can say that. And the minima stochastic gradient descent, it's just doing gradient descent on, let's say, random sample of your batch somehow, right, instead of all the whole batch, just to speed up the computation. And you have to complete this code. You have all the formulas and the shapes of all the matrices you will be using. So the equation without the momentum is this. The equation with the momentum is this. So you can try both, right? with the momentum, it will kind of speed up your training. I mean, speed up how fast you reach, I mean, the global minima, I mean, for your training. And I think here there should be kind of paper, not here. I mean, you can look at the papers online. Yeah, the papers for the batch normalization. Then you have to implement some regularization techniques, actually, so they can prevent overfitting in neural network and thus improve accuracy of a deep learning model. And I mean, from the past experience, actually, this part is kind of the most hard part. So I really uh, encourage you actually to finish everything quickly before coming here, because for the batch normalization, actually, there are really crazy equations you need to implement, and you really need to be debugging, look at the shapes, and yeah. So you have to spend a lot of time here, right? And if you can do it as quick as possible, it will help you gain some time. And the professor will definitely explain all these equations in class. So, I mean, please pay attention to that. So you have to complete this code. Everything related to the shapes are here. And I think the forward function is kind of straightforward, right? It's really simple, but add its on random sample of, I mean, your batch data that you are sending for training. So, I mean, doing the backpropagation to those sample, actually, that's what bring a kind of complication somehow. And you see, that's, I mean, quite a lot. So for the forward equation, it's straightforward, I said, but for the backward, you have to implement a lot of stuff. And you know that, I mean, while doing this thing, as they kind of correlated, when you make a mistake somewhere, I mean, it affects all the everything after that. And I think we have released some video in recitation about how to debug your code. So this will be really important here. I mean, when you are writing your code, I mean, debugging it, printing shapes of matrices, stopping your code, put some breakpoint. I mean, to know really what's happening so that you won't be, I mean, asking yourself, I mean, what's really happening. Yeah, yeah.
Do we have to understand all these formulas? Because there's so many, and I've never seen anything like that.
Yeah, so I think that's the goal of the course, right? So you have to understand it as much as you can. So if you are really able to implement this from scratch, I think you will be ready to go to Google somehow. So yeah, but I mean, the professor will go for it, I think, the next week. So please really pay attention and ask as much as question you want. But this is really the hard part, I mean, somehow, right? And after that, yeah, I think that's all. And if you have some question, you just come to office hour and everything will be solved. Then we go to the part 2 of the homework. Thanks.
Thanks, Romrik. Any questions on homework 1, part 1? I believe there are many questions. But the thing I would suggest is, it's like, don't quote me somewhere else, but try and understand as many formulas as you can. If you're not able to understand any formula as of now, just try and implement it according to the formula which is given. By the end of third week, or I think fourth week, I'm pretty sure all of you will be able to derive all of these formulas by yourself. So that's some assurance. Any questions for part 1? Yes.
Are we allowed to take shortcuts? For example, for 10H, NumPy has a 10H formula, so can we just use that?
No, I don't think you can do that, right? Yeah, so yeah, don't use the built-in libraries. This is sort of your own PyTorch version. That's why we call it the MyTorch. And this will get built over, over the next homeworks. So whatever you work on homework 1, that will be used in homework 2, and subsequently in homework 3 and homework 4.
I mean, but I remember NumPy and SciPy was allowed.
NumPy, you can use some of the, the NumPy functionalities like multiplication, vectorization, but not the inbuilt functions for activation function like tanh or like sigmoid. That defeats the whole purpose of making you understand how these activation functions work.
Can we use the basic functions like sum?
Yeah, some. That is going to be definitely used. I mean, that's the power of NumPy, right? Because it allows you to do vectorization operations without having to explicitly loop over these matrices.
This homework you will be using TensorDot a lot. So I'll suggest that you go to the documentation for TensorDot and see how basic matrix multiplication is done, because you won't know and you'll be like confused with the matrix, the shapes that there are. If you have any problem, debug your code, which there is a recitation on. So, yeah.
Correct.
Sorry.
Again, there is plenty of help available from all the TAs. Ramrik, you want to say something?
Yeah, please use as much as you can, in fact, right? Because if you use some loops, Python loop, it can really make your code low, and as it will be tested on autograd, it can take a lot of time if you don't use NumPy. So if you want to do anything, just think first how NumPy can do it, and then implement with NumPy. We have to speed the computation.
Is tensor dot ever covered as part of the course? Yeah.
Tensor dot will come in homework too, right? Yeah. So you don't have to use tensor dot in this homework. That will come into use in homework 2 part 1. So we'll cover in one of the recitations and labs and boot camps how tensor dot works. Any more questions? Yes.
Same restriction on what functions you can use from NumPy and stuff like that applies to part 2 as well.
In part 2? So yeah, part 2 you are free to use anything. It's sort of your playground to test around like PyTorch functions. Usually, you would prefer using PyTorch functions over NumPy functions, and you'll see, some of the functionalities that NumPy provides. It's already built in PyTorch, so you're free to use anything you want. For homework 1, part 1, I would suggest, go through the write-up once, just completely go through it once and see how much of you, really understand. Most of it, is what are the concepts that we discussed in yesterday's lab. You do a forward pass, you compute the gradients, they flow backwards. And that's based on the loss function that you calculate. And that is the difference between your predictions and your actual labels. And then you update your weights, that is, the model parameters, which is weights and biases. Once they are updated, you repeat the process. So every function that you see here, that Iman and the other TAs went over, they have one forward function, they have one backward function. So forward function is signifying that it is doing a forward pass. Backward function is you are making the gradients flow backward into the network. So most of it, as you go through the homework, it's more like intuition. But don't worry, you'll get most of the stuff as you go along in the course. Okay, and if there are no more questions, we can move on to the more fun part, which is part 2. So part 2 is where you get to be, you get to bring out your competitive side. There is a Kaggle competition. I hope all of you have joined that Kaggle competition. So this is all the part 2s of all homeworks is a Kaggle competition where you get to build your own model from scratch in PyTorch and run that model, do some like evaluation of your model, be it accuracy or some other prediction, and then post your scores and results on Kaggle. There is a leaderboard which is like visible to all the students, and that's why I say you get to bring out your competitive side. So there are different, we have several checkpoints because, part 2s generally get to be like more intensive than part 1. That's usually the case. So we have several checkpoints along the way for you to be on track in submitting it before deadline. So the first deadline for homework 1 part 2 is September 6th. That is, you have to build a very basic model and reach accuracy of 60%. So this we'll just cover, I'll just give you a very brief idea of what homework 1 part 2 is asking you to do. And to go over in more details, we can talk about it more. And you can also visit some of the office hours which are dedicated, for some of this stuff. So in part two, this is where you build a model for your own speech recognition task. You are given a bunch of speech recordings, and you have to map those speech recordings to a phoneme. Now, what is a phoneme? A phoneme is the smallest possible unit of sound. Like we have letters in the English language, A, B, C, D, E, F. How do we, find the smallest possible unit of measurement in audio? That is your phoneme. And so you have a list of speech recordings given in part two, and you have to classify which speech recording is categorized under which phoneme. So every language has a different set of phonemes. For this homework, we are using the English language, and there are a total of 40 phonemes available for you to classify. So this is a multi-class classification problem where you are given some, so again, when we are speaking, the audio which is being spoken, it's usually sound waves. Now, computer cannot understand sound waves, so we have to pre-process that data in a format where the computers can understand or your model can understand. So we convert those audio waveforms into spectrograms. This is MFCCs. Now, how we do that processing, it's not part of this course. That is like, pre-processing your data. But if any of you are like interested in knowing about that, there is a Piazza post on how we exactly go about creating these MFCCs from raw speech signals. So you can reach out to that. You can refer to that Piazza post if you want to know more about that. But for this homework, since the goal is to build your own deep learning model, we have already pre-processed those audio signals and given you these MFCCs. So now your task is to pass on these MFCCs through your neural network and get the output predictions. That's all you have to do. And for that to happen, your model needs to take some set of inputs in some shape. You have to figure out what the shape would be. You can go through the write-up to figure out what exactly the shape your model will take. And then what you see on the slide here is one sample architecture. So we discussed like the neural network architectures in yesterday's REST station. That was one basic one with one hidden layer. This is also pretty much the same. You have one hidden layer, one output layer, and one input layer. Now, the challenge of this homework will come into the picture when you go to the second portion of this homework. So like when you have reached the low cutoff, which is 60% accuracy, once all of you have done that, we'll evaluate the results. We'll release 3 more cutoffs, which is the low cutoff, the medium cutoff, and the high cutoff. So in order to reach high cutoff, you will have to architect or come up with your own architecture or your own design of the model. That could be anything. We'll talk about what kind of patterns and what kind of architectures there are, which are popularly used in MLPs. But I think that's part of like next week's hackathon. But that's the basic idea. What you have to do in part two of this homework, you have your MFCCs, forward pass it through your network, get the output, get the accuracy score, submit on Kaggle. And this is how the workflow is going to look like. You have to download the data set from Kaggle. So the notebook that we have given you already has the command to download that data set from Kaggle. So you simply run that cell. The data set will be downloaded. Then you have to load that data set into data loaders, again, because you have to pass in your data in batches to your model to increase the efficiency and the training time of your model. So if you're not gone through the data loaders REST station, that's REST station 0. If you're not gone through it, I would highly recommend before starting with implementing the data loader for this part, go through that REST station once so that you better understand how batches are formed and how those are passed into your model. Now, once you do that, once you have prepared your data for sending it into your neural networks, that's when you start training your model. Now, there are 2 terms here. One is the hyperparameters. I briefly touched this term in yesterday's REST station. Hyperparameters are some of the settings in your model that you fine-tune and tweak so that in order to increase the efficiency of your model. There are a bunch of hyperparameter settings. We'll go over some of these settings in, I guess, it's already mentioned here, like, what is the model architecture? What is the learning rate of your model? What kind of optimizer you are going to use for updating the weights and biases of your model. You have the scheduler, and there are a few more, hyperparameters available for you to, play around with. And I think most of them are given in the write-up. So when you train and test your model, you get, a verification or evaluation accuracy of your model. You will run it over, a few epochs. If you see, your model performance is not improving, you will go back, do a restart of the entire thing with the different settings of hyperparameters. And this is more, again, a sort of an experiment that you have to do. And some hyperparameters will work, some will not. And it is your responsibility as part of this homework to figure out which set of hyperparameters work best. Again, there is no standard rule or convention or goal where we can give you like, okay, like this specifically hyperparameter will work. It depends on a lot of parameters, like, what kind of model architecture you have chosen, how deep is your network, how, wide is your network. So again, it's an experiment, but we have given you a few hyperparameters to start with in order to reach that low cutoff of 60% accuracy. And that's pretty much it. So on WANDB, I hope you have created your account on WANDB. So all of the metrics that your model is outputting, like the accuracy, the validation accuracy, the training accuracy, the learning rate, how is it improving or decreasing over a few epochs, all of that gets logged in your WANDB, and that is very helpful because you will find that maybe some settings worked better than the other ones, and you might have to go to the previous model and that settings. It is cumbersome to find those settings if you have not saving it or logging it somewhere, and WANDB is the best platform to do that. So this is your workflow, how the workflow is going to look like. You load your data set, you build your model architecture, you pass the data through your model, get the accuracy, and see how it is improving over the epochs. If it is not, go back, change a few settings, and try again. Make sense? This is, again, if you want to understand more about how the shapes are going to be handled by your model. Again, the raw speech signal, which is the waveform, the audio waveform, in order to be processed by your model, it is passed, we do some sort of transformation, specifically the short time Fourier transformation, because there are many frequencies involved in your audio speech signal. In order to better analyze them, we have to sort of perform this step. And that's how we get the MFCCs. Again, if you want to know how this is done, the exact steps, it's mentioned on the Piazza note. I don't remember the Piazza note number, but I can give it to you after the session. These are the phonemes that you'll play around with in this homework. So there are a total of, I think, 42 here. But you don't have to count the SOS and the EOS phonemes, because that's just used to mark the end of sequence and the start of sequence. Those are not actually phonemes. So excluding that, you'll have around exactly 40 phonemes. So this, this is again a multi-class classification problem where you will classify which speech recording corresponds to which phoneme out of this list. This is part of the structure of your data set that is given in the starter notebook. So again, we have given useful comments along the way to help you out in identifying what you have to do in each step, like figure out the shape, figure out the operation. This is just to help you get started with completing this part. Just follow directly all the comments. You'll be able to code most of this stuff. Once you have done you have loaded or transformed your data set, this is the same thing. You have to do it for MFCCs and transcript for your training. Once you have done that, again, the next part would be creating your model architecture. And that's exactly the same as we went in yesterday's recitation. You have to create a class for your network. You'll have to define a self.layers variable. You'll have layers in that variable. initialize that architecture. Once you do that, whatever data you have loaded here or, prepared for your model, you pass it through the model architecture that you coded up. And I don't know how to explain this slide though. It's like, tuning hyperparameters is a challenging task. It might seem trivial, like, you just have to, do a few tweaks here and there. That's pretty much it. But given the amount of hyperparameters that we have, the combinations of, different hyperparameters goes actually to a very large number. So the main challenge in today's, research field also is like, if we talk about AGI, I've heard, I've read somewhere that AGI is just a hyper-tuning parameter away. It's just, that close. But again, that's one of the challenges of hyperparameters tuning. You have to, figure out which set of combinations will work better for your model. And so ablations is again one set of the hyperparameters that you choose to run your model on. That's called ablation. You will have to come up with a bunch of ablations to see which ablation or which set of parameters work best for your model. And to do that, because you'll be running many ablations for your models, it's better to log them in a file. So we have already given you a sample Excel file. You can download it from the write-up. It's best whenever you have fixed one set of hyperparameters and done like a run of your model, whatever the result of that run is, just log it in that Excel file. So that whenever because when you work in groups, the task will get so daunting at one time that you'll not be able to do testing of each and every hyperparameter. So you will have to distribute tasks among your team members. Okay, you try this hyperparameter, I will try this hyperparameter, you try this hyperparameter. So each member will try a specific set of hyperparameters, and to keep the entire team on loop, it's best that each member logs that somewhere in an Excel file. And we'll also ask for this ablation log file at the end of at the end of the deadline for submission. So please maintain an ablation file. It will also help your team members.
Is that great? We get a grade for turning that in?
There is no grade. It's just it's just best practice. And this is a view from WAN-DB. So whenever you are logging your matrix in WAN-DB, sort of these are the graphs that it will produce, like validation loss, validation accuracy. You can already see by given the number of lines here that we have already run so many runs of the model, and you can see some are performing well, some are not performing that well. So in order to identify which set of hyperparameters work, it is again a very good practice to log all of these metrics in your WAN-DB account. So that's pretty much it on part 2. You have, first your task is to complete the code, which is given in the starter notebook. We have given you comments that will help you get, started with the coding part. Try and reach the very low cutoff accuracy, which is 60%. And if you run into any of the issues, just feel free to reach out to any of the TAs. We have many office hours to help you guys out. My advice would be to reach the very low cutoff, just try out with a very simple architecture. You don't have to do any rocket science with the architecture. Just use very basic, simple architecture, even the one that we tried in yesterday's recitation here. Any questions? Yes.
So, do you mean that even with the basic architecture, we'll be able to reach 60%?
I cannot guarantee that because that will depend on how you have implemented other portions of your notebook. But if you follow all the instructions given in the notebook with a very simple architecture, you should be able to reach 60%. That is why we have given it as a very low cutoff accuracy.
Follow. Yes. So I'm getting a very good training and validation error, but the submission is 5%. So is that something that I'm doing wrong somewhere in my code?
So yeah, so just to clarify, are you submitting, so the submission format is you'll have all the frames IDs corresponding to the phoneme labels. That's the format you're following. Then you can, reach out to one of the TAs and we'll see, what's going on. Yes.
So you said with that one file, we should keep one for 18 for the study team, right?
Yes.
And doesn't it mean that we would have the same architecture, or we should keep different parts of it for different architectures?
Yeah, not really, so in order to reach, the higher cutoffs, there are many architectures that could work. That's what I said, when I said, we don't have a single specific set of hyperparameters that will help you cross the high cutoff. There can be many. And it's your job to, figure out which set works best for you.
So the use case for that part of the team would be to see just hypothetically what kind of changes in hyperparameters would work for different architectures.
Yes.
Not necessarily for these.
It could be that as well. Again, that's, part of the fun as well, because, there are so many hyperparameters to choose from. You will eventually start with a few. You'll assign your team members okay, you try the architecture, I'll try the learning rate. And then, you have to, approach it in a very, strategically manner. You might have to fix, okay, this architecture seems to be working. Now let's fix the architecture and move on to the other hyperparameters. And, you build on that.
So if we end up using the same architecture, it won't be fine.
No, absolutely not. Yeah. Again, like Sarthak mentioned, there are many, many ways of implementing the same architecture in different ways. Okay, that finishes up bootcamp for homework 1. Any questions?
Question from the Zoom.
Yeah.
Sorry, I may miss some point. Can you explain what is the domain knowledge?
So domain knowledge is, again, the concepts that you'll gain from the lectures. You'll see, as you proceed along with the lectures, you'll get more and more help in your homeworks, especially for homework 1, because, homework 1 and sort of the lectures take time to align. And as you attend more lectures, you'll see, it will help you with the, reaching the high cutoffs for this homework. So that's what it means by domain knowledge.
Okay, thank you.
Okay. So have you guys formed your study groups? Yes? No? Yes. Show of hands who have done it. Okay. So this is a great chance to meet your fellow, batchmates. And also, if some of you haven't formed study groups or project groups, this is a good time to meet the people and see if you click and form groups immediately, because you will be assigned specific TAs for your study groups and your project groups as well. So the sooner you do it, the better it is.
How many people can be there in the study?
I'm sorry?
How many people should the study group contain?
It's 4. I think it's 4, right?
Capped at 4 can be.
I think it is capped at 4. Yeah. Okay. I don't know about where the pizza is. Pizza's on the way. The pizza's on the way. Good news.